Okay, good morning, everyone. Let's continue on with our discussion for AC analysis. See, 1, 2, 3, 4, 5, 6, 7. It's like a private tutoring session. It's about the same number of students I had when I began the previous section. Anyway, important topic. It's about a 20 to 25 point problem in the final exam. So let's see, where did we stop? We stopped right here. Oh, that's 321, sorry. This is S201. And let's go to the right section. Okay. So just a brief recap. When you have an AC source and you apply it to a circuit containing resistors, inductors, and capacitors, we have to solve differential equations, right? Time varying signals. The capacitor and inductor also store energy. So their voltage and current relationships are dependent on time. Hence, we have to solve differential equations, derivatives, integrals. So to make the math less complex or make the math a bit easier, we use complex numbers. And we represent both the components as complex numbers or complex quantities and the source also as a complex quantity. The source is represented by a rotating vector in the complex plane. That vector is known as a phasor. It has two quantities to describe it, which is the magnitude, the length of the vector and the angle it makes with the real axis. That phasor can be written directly from the time varying expression. The length of the vector is given by the magnitude of that waveform or the peak value of the waveform Vm, and the phase angle of the vector is given by the phase of that waveform. Omega, the frequency, is kept separate because there is no need for the information of omega in a frequency domain representation. Omega is the angular velocity or the angular frequency. Again, it's a rotating vector. So omega describes the speed of rotation. Okay. One other important thing was that we have to have the expression in cosine format in order to write the phasor directly. If it is in sine format, then you subtract 90 degrees from the phase angle. So if it was given to you as sine omega t plus 50, it would become cos of omega t plus 50 minus 90. So it would become cos omega t minus 40. Okay. So the expression has to be in cosine format. All we do is subtract 90 degrees from the phase angle. And we'll see that in the example. Okay, we'll see that in the example. So that was for the source. What do we do about components? Seriously, did I? Oh, I didn't switch over. Let's see. Section 2. There we go. All right, so phase and this expression must be in cosine. You would use the expression sine x is equal to cos of x minus 90, meaning you subtract 90 degrees from the phase angle. Okay, subtract 90 degrees from the phase angle. Okay, components R, L, and C. Well, it's a bit different. Inductor and capacitor are energy storage devices. They store energy and they release it back into the circuit at a later period in time. When they store energy, remember the property of an inductor or a capacitor. When they store energy in an inductor, it gives rise to an opposing EMF or an opposing voltage, meaning when current comes into the inductor, it stores it in the magnetic field. That stored energy gives rise to a voltage. That voltage has polarity that opposes any change in the incoming current. As long as the current remains constant or steady, meaning DC, the inductor behaves like a short circuit. The moment you start to change that current, that stored energy is going to oppose any change in that current. Okay, so for DC, the inductor behaves like a short circuit. When you start to change it, the opposition appears. That opposition is described as reactance. Resistance is a term that you're familiar with. When you have electrons passing through a piece of material, allows the conduction of that electron, hence a conductor. Any opposition to the passage of that electron is termed as resistance. So it is direct opposition. That direct opposition is termed as resistance. Reactance, I like to call it as indirect opposition, meaning it allows the passage of current without any problem, but the moment you start to change the value of that current, it starts to oppose. And that is termed as reactance. Same thing for a capacitor. Capacitor, if you apply a constant DC voltage, it charges up the capacitor. When capacitor reaches full charge, it behaves like a, anyone? Open circuit. No more current can flow through. The voltage is maximum, but current goes to zero. But what happens when you start to change that voltage? If you start to change the voltage, the capacitor now starts charging or discharging in the other direction. So now current starts to flow. So capacitor behaves exactly the opposite. When you start changing the voltage, it opposes the change in voltage, but it causes the current to flow in that circuit. The reason I'm talking about that, again, that is represented by the term called reactance, noted by uppercase X. Uppercase X. For an inductor, what does it, well, for both inductors and capacitors, what does it mean when you change the value? You're talking about an AC signal. So if you change it slowly or change it and measure it, that change is measured in terms of frequency. So the faster you change, the more the opposition from the inductor. And in a capacitor, the faster you change, the more current flows through the capacitor or through the circuit. So for an inductor, the reactance increases when the change is high, or when it changes much more frequently, the frequency is high, so the reactance is high. The opposition is high, so the reactance is high. For a capacitor, when it doesn't change, it behaves like an open circuit. There is no current flowing through the circuit. But the moment it starts to change, current flows to the circuit. So the faster it changes, the lower the opposition in that capacitor. So in terms of frequency, a inductor reactance noted by XL can be given as 2 pi FL. So XL is directly proportional to frequency. The faster the current, incoming current changes, the higher the frequency, and the higher the frequency, the higher the reactance of that capacitor. And I mean, higher for the inductor. For the capacitor is exactly the opposite. You have 1 over 2 pi FC. So it is inversely proportional to the incoming frequency. And you can easily use these equations to describe what you already learned in chapter 3. For DC, F is 0. So if F is 0, opposition is 0, short circuit. For a capacitor, when F is 0, opposition is infinite, open circuit. So for DC, it behaves like an open circuit. Inductor behaves like a short circuit. Now, we again use complex numbers to describe this quantity. Okay, resistance is direct opposition, reactance is indirect opposition. To make the math easier, we describe it using complex numbers as a vector quantity, as a vector. This is not a phasor, okay? This is simply a mathematical representation. And the total sum of the pure resistance and the reactance is represented by a term known as impedance Z. And Z in mathematical terms is described by the real number for resistance and the imaginary for reactance. And hence you will often use or hear or read the term or the phrase imaginary reactance. Okay, when you read the words imaginary reactance, it is not imaginary in physical terms. Okay, it is imaginary in mathematical terms. So it's not just floating in the air that someone has just come up with. Okay, it is imaginary in mathematical terms. So R plus Jx, complex quantity with rectangular coordinates. Resistance R on the x-axis, x, imaginary x on the y-axis. Okay, so R plus Jx. And it is a vector, so when you plot it, and you extend the real and imaginary portions, you can write the impedance with a magnitude and a phase angle theta z. And we can describe a right angle triangle using the three sides. Z, R, and X is known as the impedance triangle. The phase angle it makes with the real axis is also described as the phase of the impedance, theta z. The units for all three are the same, ohms. And so is the symbol. The symbol for all three is the same symbol that we have used for resistance. So R, J, and X, I'm sorry, R, X, and Z all are represented by using the same symbol and the same units. Impedance again signifies opposition. So the most common place where you would actually come across this is in audio engineering. If you look at the spec sheet for your speakers or your AV receivers or your headphones, Bluetooth headphones, even something like this, it'll term the impedance of the speaker because the speaker has a coil. The coil is an inductor, or electrically is represented as an inductor. So headphones typically have 32 ohms of impedance. Speakers that you buy off the shelf typically have 8 ohms impedance. That, of course, is not constant. That impedance would change depending on the frequency, right? If the frequency is high, the impedance is going to increase. If the frequency is low, the impedance is going to decrease. So 32 ohms and 8 ohms, that's kind of like a typical average value. Okay, questions? Any questions at all? Any questions at all?
So, Professor?
Do you have any questions? Anyone?
Yeah, Professor.
Yeah.
So conceptually, what's like an analogy that you can give us for impedance and reactance?
Analogy for an impedance?
And reactance, yeah. Is there one that like is similar to like the pipes with amperage and voltage?
Like a mechanical analogy? I've actually never thought about it.
Yeah.
That's a good question, though. I don't have an answer right now. Let me think on it. Let me see if I can find a good analogy example.
Okay, all right.
All right. Let's see. Oh, any other questions before we talk about the equations? Okay, so said that XL and XC are directly and inversely proportional to frequency F, right? Omega, the angular frequency, is given by the equation 2 pi F. So we can write the equations for ZL and ZC directly as J omega L and 1 over J omega C. Okay. Resistor R behaves exactly the same way for AC as it does for DC. Yes. The imaginary number. So in electrical engineering, I is reserved for current, so we use J for the imaginary number. So impedance for a resistor would be R plus JXR. But for a resistor, it only has pure resistance. Because it does not store any energy, a resistor does not have any reactance. So the impedance of a resistor is simply the resistor itself, R. In fact, there is no such thing as ZR. This is just something I use for teaching purposes. In AC analysis, we simply use R because it behaves exactly the same way. No energy storage. ZL and ZC, however, are different. You would have RL plus JXL. For an ideal inductor, RL, the resistance of the inductor, is going to be 0. So it's simply JXL. And ZC is exactly the same way. Capacitor resistance plus 1 over J XC gives you 1 over JXC minus JXC. So 1 over J can be written as J over J. So it gives J over J square, J over minus 1, and hence minus J. So all of this complex math is not just something, obviously it's not just for electrical engineering, right? The math existed and the engineers and scientists took that math and applied it to solve AC analysis. So as engineers in your own field, you would use the imaginary number I for some of your calculations. If you have not already done so, you might encounter it in the future. So this is something that you should pay attention to because, again, you will, at some point in your career, you would end up using these kind of calculations. Yes. Yes. Yep. So that's why 1 over J can be described as 1 over J times J over J. You get J square minus 1 minus J. Or minus I. If you so 1 over I would give you minus I. Yeah. Okay. So in terms of frequency, we have ZL is J omega L and ZC is 1 over J omega C. It's basically JXL and 1 over J times XC. XC is 1 over omega C. XL is omega L. In terms of frequency, omega is 2 pi F. So it becomes 2 pi FL and 2 pi FC. Okay. So those are rectangular coordinates. If I wanted to write the polar coordinates, it would simply become omega L with the angle of plus 90. And here it would become 1 over omega C with the angle of minus 90. And I will talk about how those phase angles come into play. All right, any questions before we get into the angles? Okay. So remember, I mentioned or I stated several times that we use complex numbers to make the math less complex, right? If I wanted to find the voltage or current for a inductor, for let's say, for example, what do we have to do? We have to, voltage for an inductor is L di over dt. So it's the derivative of the current. Now it's a time varying current like cos x or sin x, then you have to find the derivative of that. If you solve for the voltage and current in a circuit, you would now have a differential equation to solve. But if you use complex numbers, you don't have to do any of that. You can apply all of your techniques and all the equations that we learned earlier. Ohm's law is V equals IZ for AC circuits. For DC, we learned V equals IR. Z takes the place of R because you are now representing complex quantity. So VR simply becomes IR times R. VL, instead of being the derivative of the current, is simply the product of the current and the impedance. Same thing with the capacitor. Instead of the capacitor being integration or integral of the current, it simply is the product of the capacitor current and the impedance of the capacitor. All of the equations that we learned apply just as well. The only difference is the quantities are now complex numbers. So all of the currents and voltages are now complex numbers, but you apply those exactly the same way. So impedance Z can be written as V over I. ZL becomes VL or IL. ZC is VC over IC. KVL, KCL, mesh current, node voltage, everything works just fine. How many of you are taking the lab? Just 1, 2, 3. Okay. You perform lab 6, or did you all skip over that? You did, right? So in lab 6, for those of you who are not taking the lab is about RLC circuits, resistor, inductor, capacitor. We apply an AC source to that circuit, and you measure the voltage across the 3 components. Then you take those measured voltages and you plot a phasor diagram. But if you take those voltages and add them up, KVL would not work, because when we take a meter and we measure the voltages, what are we doing? All we measure are the magnitudes. We don't get any information about the phase angle. So if you simply take those measured values and add them up, like VR plus VL plus VC, KVL would not work. We need to take phase angles into account, and hence the complex vector representation. If we have the phase angles, then KVL would work. And we can try that out with any problem that we'll solve. Now, straightforward enough, Z is V over I, right? In an inductor and a capacitor, energy transfer takes place. And because of that energy transfer, there is a phase difference between the voltage and the current for an inductor and a capacitor, respectively. There's a mathematical derivation. I usually don't do that for 201 classes. Straightforward, like 3 steps. You take a AC voltage, you apply it to an inductor, and you solve for the voltage and current. And it turns out that for an inductor, the voltage is ahead of the current. Meaning the inductor voltage VL is ahead of the current IL. When we say ahead, behind, lags, or leads, what are we talking about? Phase. We're talking about phase. So there is a phase shift or a phase difference between VL and IL. It's the same for a capacitor, but for a capacitor, the current is ahead of the voltage. And in both cases, the phase shift or the phase difference is 90 degrees. Okay, it's 90 degrees. Again, think about it. Voltage for an inductor, V is L di over dt. If you apply a sinusoidal waveform like sine x or cos x, and you take the derivative of sine and cosine, you're going to get minus 90. Once you solve it, you get phase difference of VL and IL of 90 degrees. Now, when we say voltage is ahead of the current and current is ahead of the voltage, what we're referring to is the voltage and current for that specific component. That specific component only. So if there are multiple inductors in a circuit, the voltage for one inductor is not going to be 90 degrees ahead or behind the current for another inductor. Okay, you have to refer to the current and voltage for one single particular component. That is another point of error I've seen students make in the past. There's a mnemonic that I use that helps me remember which is which. Anyone hear this before? Eli the Iceman, named after Eli Manning because he's got ice in his veins. Not really. This mnemonic's been around for a long time. You know what L stands for? You know what C stands for? You know what I stands for? E is for electromotive force or voltage. So in an inductor, the voltage is ahead of the current, or voltage comes before the current. And in a capacitor, the current comes before the voltage. And in both cases, it is 90 degrees. It's 90 degrees. So now, think about the math that we perform with complex numbers, or with vector quantities. We establish ZL is VL over IL, ZC is VC over IC. We're performing division of two complex numbers. Again, vector representation, right? R is the length of the vector, theta is the phase angle it makes with the real axis. The projection of the vector on the real and imaginary axis gives us the rectangular coordinates. So R with the phase angle theta is A plus or minus JB. You'll perform this kind of math for this entire chapter. And the four mathematical operations, you can perform it in any coordinates you want, right? Especially if you have a programmable calculator, it does all the work. But if you're doing it manually, then performing an addition or subtraction is easier if you have rectangular coordinates, and multiplication as division is easier if you use polar coordinates. And so you transform back and forth between the two. How many of you have reviewed the complex number handout on Canvas? No one yet? At least one person? Two people? It is absolutely essential you know how to do that, okay? And everyone has different devices, different calculators. I don't have one. My calculator is from the 90s. It is a scientific engineering calculator, but it's not, we were not permitted to have programmable calculators with us. So we, at least for me, I cannot do or cannot perform complex equations directly. I need to switch back and forth between polar and rectangular. So if you have ZL over IL, what do we do? It has both magnitude and it has phase, and theta IL. How do we solve this? Anyone? The magnitudes are divided. The phase angles get subtracted. And that would be the answer. So you would get magnitude VL divided by magnitude IL. The phase angles get divided. Hence, theta V minus theta I. Phase angle of the voltage minus phase of the current. Phase of the voltage for an inductor is ahead of the current by plus 90. So impedance for a inductor will always have plus 90. Theta of ZL is always plus 90. Same thing for a capacitor. A capacitor, ZC is VC over IC. And so you get magnitude of VC divided by magnitude of the capacitor current. Phase angles get subtracted. And therefore, theta of ZC is always minus 90. In terms of phasor diagrams or vector representation of the phasor diagram, plus 90 will be pointing straight up. If this is 0, 0, plus 90 points straight up. And minus 90 points straight down. Hence minus j. It's on the negative imaginary axis. Does that make sense now? Mathematical terms. Again, remember, it's a vector, right? Vector rotates counterclockwise in this direction. So if you count the angle in a counterclockwise direction, it is positive. If you go clockwise, then it's negative. So plus 90 pointing straight up, minus 90 pointing straight down. Plus j, minus j. Or 1 over j. And hence the representation j omega L plus 90, 1 over j omega c, or with an angle of minus 90. And that's why we have those kind of equations. All right, any questions? This is also going to be very important for AC power, which we will tackle next week. Okay, so for inductor and capacitor, AC power, it's a different kind of power. Again, the reason is because it stores energy, right? So energy flows in, energy flows out constantly between the inductor and the capacitor. That is known as reactive power. And reactive power is a complex quantity. Sorry, AC power is a complex quantity. Power for an inductor will have positive 90 degrees. Power for a capacitor will be minus 90. So lots of concepts in last class and in this class. Okay, questions? Any questions at all? Impedances in series and parallel. Impedances in series and parallel add up the same way that you would add up resistors. Meaning impedances in series simply add up. Impedances in parallel, you'd have to take the reciprocals and take the reciprocal of the resulting sum. Important to note that we cannot combine resistors, inductors, and capacitors, but we can combine impedances of resistors, inductors, and capacitors. Right? You cannot add R plus L. You cannot add L plus C, but we can certainly add ZL plus ZC or ZL plus ZC plus R, because impedance is the same quantity, right? So you can add those up. So we cannot add up R, L, and C, but we can add up R, ZL, and ZC. And they add up the exact same way as resistors in series and parallel. The only thing we have to be careful is capacitors, pure capacitances, add up the opposite way of resistors. But the impedance of a capacitor will add up exactly the same way as resistors. I've also seen students make that mistake in the past, so always try to keep harping on that. And we will practice this in problems. Here are a few terms that students should be familiar with. We will not solve any problems using these terms, but as an engineer, you should be familiar if someone talks about these terms in a meeting, or you might be doing a project, and someone talks about conductance, admittance, or susceptance, you should be aware of what they're talking about. So these are all reciprocals. We started off the chapter Basic Physics by talking about conductors, right? Passage of electrons in a piece of material, meaning we're talking about conduction of electrons. A material that allows easy conduction is known as conductor. Any opposition to the passage of electrons is termed as resistance. So resistance and conductance are reciprocals of each other. Similarly, reactance and impedance also have reciprocals. They are termed as susceptance and admittance. So why G, and B. Y, G, and B. The units for impedance, resistance, and reactance is ohms. For the reciprocals, it's Siemens. And it's simply 1 over Y, 1 over G, 1 over B. Okay. Now, if you have components in parallel, that's where it is very useful to use the reciprocals. Because instead of taking the reciprocal of each individually, if you just find the reciprocals at the beginning, all you'd have to do is, instead of taking the sum of the reciprocals, you'd simply find Y is equal to G1 plus G2 plus B, and so on and so forth. It also makes it easier when you want to find current division. If you want to apply current division, using reciprocals makes it very, very easy. Okay, for E major classes, we perform some problems using these reciprocal quantities. For non-major classes, we typically don't. Okay, any questions before we move into examples? There's actually plenty of time. And I was a bit delayed in the first section. We only managed to get through the first example. So, any questions? So there's lots of information, again, from the previous class and this class, but it's all about concepts, okay? Concepts of complex quantities, complex numbers. The math, the actual math is the same as what we did for the first two chapters. I mean, sorry. The techniques are the same as the first two chapters. It's the math that is slightly different because we use complex numbers. Okay, so the techniques are exactly the same. So no difference whatsoever. If you apply a voltage to a resistor and an inductor, and you want to AC voltage, for instance, and you want to find the voltage across the inductor itself, you can apply voltage division, or you can calculate Ohm's law, except you are now working with complex numbers. We do not have to write a differential equation. That's the biggest thing. So there are 5 examples in here. In the first section this morning before yours, I was only able to get through the first example, and I said I will create videos for the rest of them. So I'm going to do the same thing here. I'll go over example 1, and we have time for questions. If students have any questions, they can get those answered. So let's look at example 1. What is it asking us? It is asking us to solve for Vs of t. So find the value of Vs of t. It is given as 2 separate components, 10 cos omega t plus 10 sin omega t. First thing to do is to see if it is possible to combine these 2 components together or not. And the way we do that is by looking at the frequency. If the frequencies are not the same, you cannot combine, or we cannot combine those together. Okay, they will remain as separate. They will not be, we cannot combine those. The first thing to check when you're adding or subtracting 2 components together, the frequencies must be the same. We cannot add or subtract 2 or more different signals unless their frequencies are the same. That's the first thing you need to check. That's also the principle behind noise cancellation technology. Noise cancellation technology uses a microphone to capture surrounding noise. So you'll have multiple frequencies that are captured using that microphone. Then you have an inverting amplifier, which inverts the phase by 180 degrees. Magnitude is kept the same, and you add it the same incoming signal. So when you take the incoming signal, you invert the phase and you add it to the same signal, it cancels out. Vector quantity, minus 180 or plus 180 cancels it out. Okay. But the frequencies are not the same. All you're going to get is like jangling noise. Frequencies should not be affected. Anyway, unless the problem states to solve it with a particular method, in this case, you would assume that you have to use phasor techniques, meaning you convert each of the quantities as a phasor, and then you perform complex math on it, and you get the final answer. So Vs of t if I want to write the phasor, I have to have a cosine expression. So the second one, which is sine, is going to be changed to cos omega t minus 90. Once I have both of them in cosine form, I can write the phasor directly. And this uppercase V is going to be my notation for a phasor. Magnitude of 10, phase angle 0. Magnitude of 10, phase angle minus 90. Now, if you have programmable calculators, I suggest you program this equation directly in there and you obtain the final answer. What I would do is this. I would convert this to rectangular coordinates. Converting this to rectangular coordinates gives me 10 plus j0. And this would be 0 minus j10. So 10 angle 0, 10 angle 0 means it lies on the x-axis. Angle is 0, so it lies on the x-axis. Real positive real axis with a length of 10. And 10 with the angle of minus 90 means minus 90 is right here and length of 10. So if I combine these two together, I have this kind of vector. So my vector is here. Both of them are equal. So this phase angle is 45. So the answer to that is 10 square plus 10 square. So root of 200. Vs comes out to be 14.14 with a phase angle of 45. If you have a programmable calculator, you should be able to go directly from here to here. You can go ahead and try and do this and see if you can get the exact same answer. Again, as engineers, you should be able to perform complex math on your own devices. This is something I would not be able to help you with. Everyone has a different device. I certainly do not have a programmable calculator. And now I think I'm, too old and set in my ways to actually learn something new. I shouldn't say that, obviously, but one of these days, maybe I'll upgrade and get a programmable one and learn how to perform it directly. Anyway, the way it pertains to your problem solving skills is you should be familiar with the process. I hope this makes sense, right? But if you have a tool at your disposal that will save you time, then why go through all of that, right? You should go directly from this step to this step. But you need to be an expert or very confident in your skills, because if you make an error anywhere in programming that equation, your final answer is going to be incorrect, because you would have done the setup of the problem, you would have your equation, and then you'd have your final answer directly. If your final answer is incorrect, I cannot give you partial credit because there is no work in the middle. Okay, so if you want partial credit, you should show some work in the middle, because let's say you have you have this kind of equation, the setup is fine, you would get some points for that, and then you go final answer. Your final answer is incorrect. There's nothing else I can give you. I can give you some points there, but nothing here. But if you show some work in the middle, even though in real life you would not, want to waste that much time showing all the steps. In an assessment, I will be able to give you partial credit. Okay, does that make sense? Your answer is still not complete because the original question asked for Vs of t as a function of time. So the final answer cannot be in phasor form. It has to be in the function of time or the time domain response. You have to perform an inverse phasor transform, which is not as complicated as it sounds. And you simply write the final answer Vs of t as a magnitude of 14.14, and the inverse phasor transform will be a cosine expression. The frequency does not change. So you go back to the original frequency, cos of omega t, and this is actually minus 45, not plus. So it seems like nobody is solving this. Nobody has solved this equation because nobody brought this up. Phase angle would be minus 45. So 14.14 cosine or cos omega t minus 45 degrees volts. That would be your absolute final answer. Absolute final answer. Okay, questions? Any questions at all? All right, then there are 4 minutes left. We'll end the class here for today. I will most likely solve examples 2, 3, 4, and perhaps even 5 and post a video sometime later today. And quiz on Monday based on this chapter, AC analysis. I will post the details of the quiz sometime either today or tomorrow. But in-class announcement, quiz as usual on Monday. So quiz 6 on Monday based on chapter 5. All right, have a good weekend. And if you need to see me for office hours, I will be in my office later today. And if you want to see me on Zoom over the weekend, simply send me an email and we'll just, set up a time and we'll get your questions answered.
Wait, just
yeah.
one quick question. So chapter 5, the quiz is going to be on all of chapter 5, or are there specific parts that we should focus on?
Well, I haven't completely decided yet.
Okay.
So maybe examples, maybe up to examples 1, 2, 3, 4, perhaps.
Okay.
Yeah. All right. Wish you all a good weekend and see you all on Monday. See you. Hey, good luck with registration for those of you who are trying to get into classes. Thank you.